Gene is a little worse because it's part of the cyclotron.
Government's worse than the local government, I guess?
Well, it's more about a federal type environment versus an academic.
Yeah, that's tricky. Actually, I should, since we brought up the topic, you should be aware that I will not be here the week of the 17th through 15th, whatever, April 17th. Yeah, exactly.
That's literally the 1 week where I'm going to do anything that matters for points, and you should know.
Yeah. Oh yeah, certification. Yeah, I thought about doing that and then I'm locked out. I think Justin concluded too, and they don't want to do it. Yeah, concluded. Yeah,
I'm a 5th grader.
but I guess that's a phrase I picked up when I was younger, and I guess I could. He said it was shitty. Would you prefer me to use bad term, or that it's shitty to do it while you're doing good terms? I can use childish insults when I want to. I swear, like a sailor enough. Is this the? There was like a summer program in teaching. Are you going on that?
Do you remember the name of it? Because
right now
I have not planned anything.
I'm going to. There was a program I thought about going to, but then Justin was like, it doesn't really work when stuff happens during finals.
Okay.
And it was like, and it was the application period was last semester. Keep these things straight. Yeah. Okay. I will be going to Mesa, I think.
Oh.
I will also be getting up.
You'll be going to Mesa?
Mesa School.
Like Arizona?
No, actually, I'm not sure where it is. But yeah, I'll be going to Mesa School for over the summer.
Cool.
I assume I am. I suppose.
Santa Barbara, let's go.
Yep. Are you going there?
No, I don't use Mesa.
Yeah. It's terrible.
Well,
even though my advisor actually made it.
I'm more interested in what happens when the star dies, unless it's life before.
Yeah.
Because while it does have an influence on the overall structure, not many gravitational waves are emitted that we know of during just its main sequence or some other time gravitational wave.
Yeah.
But I heard good things about this.
It's according to Ed, that's what I'm going to be working on. So.
Great. Sounds useful.
Yeah. Also, I think it also has something to do with him being the developer of it. So. Yeah. Or an old. Yeah.
Oh my God.
It's National Chocolate Caramel
Day. Yeah, we got federal holiday. Yeah. How could we be working when it's National
Chocolate
Caramel Day?
That's how I end my history. I'll end with happy. People like what National Day is. It's also National Nurses Day, National Poultry Day, and National Let's Laugh.
Should end it with all of them.
Let's laugh at all the national days.
What's this though?
They got to you.
Yeah, fair enough. Admittedly, caramel and chocolate. Sometimes if it's made well.
The Ferrero Rocher challenge. You know those like nougat bubbles.
Yeah, those.
It's like solid caramel wrapped in chocolate. You have to eat so many. Wow. Like after 2 weeks, yeah, the caramel just like puts your mouth again. Yeah, can't swing it.
Those challenges.
Alright. What are you doing there? Hey, Albert. I suppose so. Yeah. We want all the business students to come by and join us.
I think they'll understand the importance of the
Sometimes it can swap.
Steve is joining us remotely, so he's floating ahead on the screen.
Hi, Steve. Hi, Steve.
I think he's muted himself. Probably walked away. Having a beer. All right. I don't have as much as normal today, which I'm sure breaks your heart. Partly, well, mostly because I've been feeling under the weather. And so I just haven't put together as much as I normally do. So when we're done with the lecture part for today, I thought we could start talking about the project and looking at the code that I want to extend. And it's new to me. I mean, I've used it like once, right? But it's a really nice piece of software written by one of my close collaborators, and he is so good at software. The guy's insane. And so the software is really nice, and he's got a manual, like a user guide for it, really nice documentation. I think it's going to be pretty straightforward, but we can talk about that, and then we can talk about the steps that we need to take to add a general relativistic solver to it. I think it'll be straightforward to do the easiest thing with the flat space-time fixed metric, which will be the first step. We'll talk about that.
So we actually are going to get a publication.
I hope so. I mean, we can talk about the scope that takes. So he has a publication on this code in the Journal of Open Source Software, and that to me is like we could at least do something like that, right? Here's this GR solver for this Python code. We could at least do that, and that's like citable, referenceable. It's the whole thing. And then if we do something even more fancy, maybe go higher. But I think we can absolutely get this done. Oh yeah, there's Jen. Just looking around going, who are we missing? My head's pretty fuzzy today, so watch my indices. Yeah.
Who's going to do this?
So, well, that's what we're going to talk about. Yeah, I want it to be a group effort, but I also want it to be somewhat self-organized. And so my vision on this is that we'll fork his code onto our GitHub organization that we all have, and I'll make sure that everyone's added to that so that we can hack away at it there, and then eventually we'll push it back to them for pull requests. But we'll fork and then start hacking away at it. I'll show you the code. We can take the rest of the class at the end and go through the code and come up with a plan just for that. But my hope is that you all decide amongst yourself to some extent who will do what piece of work. That way it's matched to your particular skills.
But we also have to write there.
Yeah, and then in the end we have to write. Okay, so let's finish up shock jump conditions. So today I'm going to get through just a little bit of stuff about imperfect gases in matter and then introduce radiation hydrodynamics. I think the way that the pacing is going right now, I am not going to dive into the amount of detail on radiation hydro that the book goes into. And well, I'm either going to cut a little radiation hydro or I'm going to cut magnetohydrodynamics. What are you all more interested in? I like them both. Both.
Yeah.
Both. Okay, fine. Chapter 5 will be 4 lectures. Fine. I like them both. So we'll go into detail on both. And I'll figure out something on the back end. They're not that good, Halbert. They're not that good. Okay. So ranking Begonio. Last time we derived this shock jump condition. Just to remind you, we've got the upstream side, the downstream side. This is some shock transition, which mathematically we'll treat as being infinitesimally small. And we derived conditions for the fluid flow variables, specifically like the enthalpy, the specific enthalpy, based on the strength of the shock and based on the fact that certain quantities had to be conserved. Force momentum must be conserved and baryon number must be conserved, or rest mass density must be conserved. So from that, we were able to get shock jump conditions, and in the end, I scribbled down on the board the final relationship. So the difference in the squared enthalpy on the upstream and downstream has got to be equal to upstream enthalpy over the upstream density minus downstream quantities, all times the pressure difference, the upstream minus the downstream. Yeah. Okay. So this is our Rankine-Hugoniot condition, sometimes called the Taube adiabat. Okay. So now let's derive some physical intuition from this. Specifically, we'd like to know, based on parameters of the shock, specifically how strong the shock is, how fast the shock is moving, what physical quantities tend to do. What are the jump conditions? So we can non-dimensionalize this. And when we do that, we end up with something that looks like this. I'll write the definitions for. Big H squared minus 1 is equal to delta squared y minus 1, all times big H over C. That's an eta. I'm going to do this a few times today. That's blurry. Eta plus 1, where big H is defined to be ratio of the enthalpies. Y is ratio of the pressures, upstream to downstream. And eta is the ratio of the densities, rest mass densities upstream and downstream. Like that. Oh, delta. Delta squared is equal to this pressure of the downstream divided by density downstream, enthalpy downstream. Okay? So now we can use a gamma law equation of state. So P is equal to big gamma minus 1 all times the rest mass density times the specific energy density. And make a new definition, little q, which we'll define just to be 1 over the downstream enthalpy. And if we do that, what we end up with is a new condition. Question?
So in this case, rho and rho naught are the same thing?
No.
No, they're not. Okay.
Energy. Oh, did I drop my? Sorry. They are.
Okay.
I dropped this from my notes. Thank you. here, right? Like this. It's just rest mass density. Scribble in my notes, I dropped the knots when I was deriving this. Okay. So this leads to our final condition, y gamma minus 1 plus gamma q plus 1, close bracket, all times eta squared minus q all times y times gamma plus 1 plus gamma minus 1 all times eta minus 1 minus q times y all times y plus gamma minus 1, and that must equal to 0. So taking these definitions, plugging it into this, and working it out, we end up with this. So this is a non-dimensionalized form of the Rankine-Hugoniot conditions then. And in this case, Q measures degree of relativity, let's call it. So how relativistic is the shock? Right? So if you look at Q, what is this ratio of the enthalpy? Right? So as Q goes to 1, it's non-relativistic. As Q goes to 0, it's extremely relativistic. In other words, the enthalpy becomes very, very large for an ultra-relativistic flow. Makes sense, right? The energy becomes very large. So that's the idea.
Supposed to be at least 1 over h minus.
That's right. And so as it goes to 0, as Q goes to 0, it's ultra-relativistic. Because the enthalpy gets bigger as it becomes more and more relativistic. Okay, so let me write that. So Q goes to 1 is non-relativistic. In R. Q goes to 0 is ultra-relativistic. You are like that. And then, okay, in the non-relativistic limit then, so I could take that limit, go put Q equals 1 everywhere in that equation, and it will reduce to something much simpler, and that leads to a constraint. Then I can turn this around, put Q equals 1 in here, turn it around and solve for eta, the density contrast. So for a non-relativistic shock, how does the density change as you go through the shock? And that looks like this. Y times gamma plus 1 plus gamma minus 1, like that, all over y times gamma minus 1 plus gamma plus 1. Which, if you've taken non-relativistic fluid dynamics, should be pretty familiar to you. And here, y is the shock strength. It's a measure of that shock strength, we'll call it. So if you look at this y here, right, the pressure ratios, we're going to call the shock strength. So when I drew my diagram, I had the pluses and minuses on the wrong side. Let me redraw my diagram. I mislabeled it. All right. This is the plus side, post-shock, if the shock is moving this way. There's our little z hat. And then this is the minus side. Why is shock strength? and y goes to infinity for a strong shock, such that the upstream pressure, P minus, is essentially 0, right, relative to the downstream pressure, the post-shock pressure. And then for a weak shock, y goes to 1. And that actually is the case for an acoustic wave. Might not even be a shock. It's not a shock anymore, right? Because now there's no pressure discontinuity at all. So if y goes to 1, that's actually just an acoustic wave. Pressure is continuous. We're no longer talking about a shock at all. Okay. So then, plugging this in, we find that for a strong shock, the density contrast is just gamma plus 1 over gamma minus 1. Strong, non-relativistic shock. Okay, so like for gamma equals 4/3 gas, radiation dominated, what we get? 4/3 in here plus 1, that's 7/3 divided by 1/3, right? So 7. So that's the density contrast for a strong non-relativistic shock in a radiation-dominated environment. 5/3, I think it's, what is it, 4? I think I just remember that off the top of my head. It's 5. Someone else do the math. 5/3, is that 4? So you get 8/3 and then divide by, yeah, 4. Okay, cool. I'll leave that. Do I have enough room to do this much? Maybe I do. I'm just going to erase this top line so that we still have our definitions, and that'll give me enough space to do the relativistic limit. So then, in the ultra-relativistic limit, our density contrast goes to, so again, ultra-relativistic, we're going to plug in Q of 0 in there and get a fairly simple expression for the density contrast just from solving that. And that's going to look something like this. Y times y plus gamma minus 1 all over y times gamma minus 1 plus 1, all of that square root, like that. So then, pull the same thing, stick in for a strong shock now. Okay, so, well, what do you actually, it's worth noting here. For the strong shock in a Newtonian case, right, a non-relativistic case, it asymptotes to a limiting value. The shock strength can go to infinity, right? Well, we did. And it asymptotes to a constant value. So no matter how strong the shock is, the density contrast is the same. Asymptotic. But now, if we plug in our y equals infinity into here and work that out, what we get is the following. Looks something like this. Eta is going to be equal to y over gamma minus 1, all to the 1/2. Ultra-relativistic strong shock. So that does not asymptote. It goes like the square root of the shock strength. Why? And so the harder and harder you push the shock, the greater and greater the density contrast becomes in the ultra-relativistic case. Very different from the Newtonian behavior. So the shock density contrast can expand, can increase without bound. Goes like the square root of the shock strength. Okay. So those are the shock jump conditions. Those form the basis for some of the test problems that you might use in a in hydrodynamics code, right? The most basic of which is, well, I don't know how basic it is. There's many other basic problems, but one that's very common and very useful is a shock tube problem. And in a shock tube problem, you set up a left and a right state with the discontinuity separating them, and then solve. This is sometimes called a SOD problem. And it's a good test because it's got a shock in it, which means you're exploring the fully nonlinear characteristic of the hydrodynamic equations. It's nice in, so let's talk about tests real briefly, because we're going to do some tests. Obviously, one of the things that we'll want to do if we implement a relativistic solver is to test it. The Pyro code that we're going to start from has already got some nice test problems set up in it. We might have to make some modifications to them for the relativistic case, or at least, push its limits, right? Because one of the things that we can do is stick in the shock tube problem, drive it really, really hard, drive a strong shock, and test our shock jump conditions to see if the density and pressure contrasts agree with what the analytic solutions here that we've derived from Rankin-Hugoniot give us. That's one test, right? Do we get the correct density contrast? So one, shock tube. And this is nice because it can be a purely hydrodynamic test. So you do Minkowski space, so flat space-time, and obviously the metric is fixed there, right? It's just the flat metric. And so there's no gravity part to it, in other words. It's just flat space, and so in other words, this reduces to a special relativistic test in Minkowski space. All right? And so it's a pure hydro test. That's nice because it separates out the space-time solver. That's also nice because what I envision is this is basically the first problem that we'll work towards solving because we'll ignore details of the metric, right? We'll basically write at first a special relativistic solver. That will be simpler. Of course, we'll do it in a covariant way, fully expressed with a metric. The metric will just be the flat metric. Okay. Analytic solutions in this game are rare, few and far between, but there's a few useful ones. So a couple analytic solutions, which are helpful. TOV equilibrium. So this is quasi-analytic, right? You all wrote TOV solvers. So we can come up with some initial state. You can solve it for what it should be from your TOV solver, and then stick it into your actual hydrodynamic solver and see if it maintains it, right? If you get some secular drift of the equilibrium, you know you've got some problems, right? Because it should maintain steady state. And so that's a nice test. I've actually subjected my code to this test when we implemented some GR stuff. So that's a useful one. And in this case, it has gravity, right? So you've got a space-time metric. You've got a non-flat metric. So this is now a full GR test. But the metric is fixed, right? The metric should not evolve in time. It should stay constant. And so you can do this test basically as a purely hydrodynamic test where you actually by hand fix the metric so that it can't evolve, right? And then just test your hydro, so sort of next step up from this, from the shock tube problem. And then you can implement an actual space-time evolution, right? And put this problem back in it and make sure that the space-time doesn't change. But that's actually a more stringent problem because if you've got a little bit of secular drift or a little bit of wiggle in your hydrodynamic sector, that will feed back in on the space-time because of the nonlinear coupling. And those two things will start to get out of balance and then boop, 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 unstable star explodes. Good.
So it's important to do the fluid right first.
Yeah, if you don't get the fluid right in these kinds of tests, you won't get the space-time right. But now there are problems where you could just test the space-time solver, right? Like you could TAB equals 0, right? Just take vacuum space-time. Different set of tests, right? Those, in some sense, we've already talked about, right? Does the space-time obey the constraint equations? does the space-time conserve certain quantities like the ADM mass, et cetera, et cetera. Another analytic one, which is nice, is the Oppenheimer-Schneider collapse. At this point, I can't remember, did we talk about this one in lecture? We did not talk about Oppenheimer-Schneider. So this is dust collapse. And this is actually a nice step up then from this problem. So I would actually, I'm kind of laying out what I foresee as our test problems cases, right? We start here, we get this, check mark. Great, awesome. Move on to this, with the sub-step in here being, well, actually, we don't even have to do that, an evolving space-time metric. And then the next step is this Oppenheimer-Schneider collapse. This is dust collapse. So there is matter, but it's pressureless matter, non-interacting pressureless matter, P equals 0, which simplifies things, right? And so you call it dust because dust doesn't have pressure, apparently. Unless it's charged, I don't know. But there's an analytic solution for this, and that's actually nice. The analytic solutions for this was actually used to model core-pop supernovae way back in the days, the 60s. I was trying to quote you. Because it's almost pressureless collapse. It does collapse homologously. And the nice thing about this is that it has an evolving metric. And so if we get through all of these things, we've got a covariant solver that you can do input a fixed space-time metric and get the correct solution with on some set of test problems. We can then implement some version of a space-time solver of actually evolving the metric. And that's everything that we've been talking about before we got to matter stuff, right? The evolution equations for the extrinsic curvature and the spatial metric, obeying the constraint equations, the slicing conditions, the gauge conditions, all of those things that get folded into this step, right? This is actually kind of a big step. But this is an analytic solution that we can use to model this. Okay. And then there are things like conservation, right? The tricky thing with some of these things, like Oppenheimer-Schneider collapse, it's an analytic solution in a particular choice of coordinates, right? Because choosing your coordinates is so important. But now, numerically, you can't use those coordinates. And so numerically, you have to use a different gauge choice. And so in order to actually compare them, you have to convert from your numerical gauge to the correct coordinate system used by the analytic solution of the Oppenheimer-Schneider collapse. So life is complicated, but doable. It's totally a doable thing. But you got to be aware of that, that the certain solutions and certain numerical procedures only work in certain coordinate systems, like what we've been talking about. And then the other thing that you can test is conservation of things like mass. But now, what mass is conserved is a tricky definition. The one that's usually used is the ADM mass, which is defined in the book somewhere. And also the ADM angular momentum, and then circulation, which comes from the Kelvin-Helmholtz theorem. So in plain Newtonian hydrodynamics, if you've taken a fluids class, circulation is conserved. All else being equal in the absence of other forces acting on it. If you spin the toilet keeps spinning. Only stops because, well, the water leaves, and also friction with the surface of the bowl. But in the absence of those kinds of forces, circulation is conserved. It would keep on spinning. There's a relativistic version of that as well, and you can test for that in a numerical solver to see if you're actually conserving circulation, which is another expression of just conserving angular momentum. Okay, so that's kind of what I'm thinking we'll do, at least initially with test problems. There's some other test problems that we can play around with. And this shock tube, is a family of problems. I'll show you a solution when we I'll plug in my computer and I'll pull up Pyro. Pyro's obviously already got a bunch of shock tube problems in it. But you can increase that ratio. We can test the Rankine-Hugoniot conditions to make sure the code recovers them, etc. And just, if your code runs without breaking with the shock tube problem, you're probably pretty close to right. Because it is, shocks are hard. Okay. All right, let's talk about a few other extraneous. Imperfect gases. By which I mean gases that include viscosity, conductivity, and radiation. Okay? So interesting source terms that we need to deal with, okay? So perfect gases are nice for getting analytic solutions. They're nice for implementing, you know, numerical solvers because they're simple. I can express the equation of state in a very closed and simplistic form. But most interesting problems, especially in astrophysics, are going to be some version of an imperfect gas, right? They won't be expressible as a truly perfect gas. You've got to include some interesting features, whether that's in the equation of state being complicated or at least non-perfect, or the inclusion of radiation or heat conduction or the fluid being viscous. All of these things matter in certain regimes for interesting astrophysical problems. And so how do we deal with those in a relativistic code? Viscosity. So here, the viscous part of the stress energy tensor looks like this. So I'll write this down. TAB visc is equal to -2 eta, different eta, and I'll define it, sigma AB minus zeta theta PAB, where eta is greater than or equal to 0, and that is the coefficient of shear or dynamic viscosity. Shear viscosity. That's just a coefficient, must be greater than 0. Zeta, greater than or equal to 0, is the coefficient of bulk viscosity. And theta, I'm going to run out of space, which is equal to the divergence of the 4 velocity. What's this? Anyone know what the divergence of the 4 velocity is? What's the divergence of the velocity, the spatial velocity? Shear. This is the shear, right? I'm running out of space. Am I going to need this again? Yeah, I'm going to need these again, so I'm going to keep these up here somewhere. I'll write PAB down here. I'm not going to have enough space for that. But that's okay. I'll figure it out. Okay. Let me just go ahead and do that up here so I don't get too crunched. I need more whiteboards. I need those ones that like slide up and down and halfway around the room. Okay. PAB is equal to G, the metric AB, plus tensor product of the 4 velocity. And this is called the expansion tensor. And then finally, sigma AB, which is equal to 1/2 all times expansion tensor PAC divergence. Well, that's just a gradient. Del C UB plus PBC del C UA minus 1/3 theta PAB. And this is called the projection tensor. Projecting the expansion tensor. Okay? So all of those go into our viscous part of the stress energy tensor, right? And so you can see if these coefficients are 0, well, the viscosity goes away entirely. So it's all determined by what these coefficients are, if they're greater than 0. Now, recall that the energy equation we had this before, was equal to partial derivative in time, and I'm going to write down the
simplified version of the energy equation where we assume perfect gas. Gamma to the 1/2 E star plus partial derivative in space of gamma to the 1/2 E star spatial velocity. That's a divergence, so that's a J. Now, before, our energy equation in this form was equal to 0. It was a conservation law for energy, right? But now, if we've got viscous terms, the right-hand side is no longer equal to 0. With viscous terms, we have some stuff over here. It goes like the laps, gamma to the 1/2, all over big gamma, which is the gamma law index, all times E star over the Lorentz factor W to the 1 minus gamma power, all times the quantity of 2 times eta sigma AB inner product sigma AB plus zeta theta squared. So a bit complex. Now we've got all these terms over here on the right-hand side. But again, you can see just by looking at this, if we set eta and zeta to 0, it goes away. Reduces right back to our original form of the energy equation, no problem. Okay. The fact that we've got stuff on the right-hand side of this equation implies that there's entropy generation due to viscosity. So the presence of this right-hand side implies entropy generation. So entropy is no longer conserved. This is no longer adiabatic. In other words, the presence of viscosity generates entropy. I mean, you know that. Rub your hands together, right? Okay. And then the momentum equation. In the presence of viscosity, that becomes partial in time gamma 1/2 momentum vector density plus partial J gamma 1/2 momentum vector the spatial velocity. Now this was equal to 0. No, I'm sorry. This was, hold on, not equal to 0. It's the momentum equation. Equal to minus alpha gamma 1/2 all times partial derivative in I of the pressure plus SA SB all over 2 alpha ST, the time component. I'm going to keep writing over here, pardon. Gradient of the metric, close. That's what it was equal to, right? So we had what looked like our conservation law on this side, a time derivative, a divergence of a flux, and then over here we had terms that went like the metric and metric quantities, which were our acceleration, right, our gravitational accelerations. In the presence now of viscosity, we get an extra term over here on the right-hand side, which is plus alpha gamma to the 1/2 eta sigma AB, and then gradient of the metric GAB. Extra term on the right-hand side in the presence of viscosity. Hi, Aditya. How are you? Oh, I'm going to run out of room. I knew that wasn't enough. There's a lot more terms. Hold on. I turned the page of my notes and it just kept going. I'm like, oh yeah, right. Because I was thinking, where did the derivatives go? Hold on. It's going to be the same term. That's not wrong. I'm just going to make room. All right. Let's write the rest of the terms. I'm going to cite my foggy brain. All right. Term we had. Now additional terms. A few of them. Plus 2 partial in A, all of alpha gamma to the 1/2 eta sigma IB times G the metric AB close parentheses, plus, keeps going, 1/2 alpha gamma to the 1/2 zeta theta PAB gradient I of the metric GAB. One more term, plus gradient dA, partial A, all of alpha gamma to the 1/2 zeta theta PIB GAB. Okay, so that's a lot more complicated in the presence of viscosity. Together, these equations, supplemented by the continuity equation, which doesn't change, are the relativistic Navier-Stokes equations. Right? So just like in Newtonian mechanics, if we add viscosity, we include viscosity. We go from the Euler equations to the Navier-Stokes equations. These are the relativistic versions of the Navier-Stokes equations. They're pretty tricky to solve because now the right-hand sides have temporal derivatives of my quantities, right? I've now got these temporal derivatives on this right-hand side. And that actually makes this somewhat tricky to solve. It's often done in an operator split way, where you basically take all of these source terms that result from the viscosity and keep them separated and solve the original equations essentially as they were, and then update those equations with a separate solve of these source terms. It's called operator splitting. You can use even a different integration method. It's often the case that you'll even use a lower order method to solve these viscous terms, because lower order methods tend to be a little more stable and robust. And some of these source terms can actually be pretty stiff that depend on these time derivatives, meaning that they're very sensitive to the inputs. They vary rapidly in time or to some high power of the inputs that you're giving to them. You might even solve them implicitly. So you might take those source terms off into an implicit solve and an implicit explicit scheme, an IMEX scheme, where this part is solved explicitly, this part is solved implicitly. So it gets harder. And I should note this is the compressible Navier-Stokes, right? We haven't taken the incompressible limit. So this is compressible, fully compressible viscous Navier-Stokes. Okay. And this gets used. So recently there was a paper from a friend and colleague of mine, David Radice, and he was looking at, so neutron star mergers are like all the rage. They're like a thing. Apparently they're real. But one of the interesting questions is, how does the newly formed hypermassive, perhaps, neutron star spin down, right? So you've got the merger of two neutron stars. Let's say that they're low mass enough that the remnant from their merger is below the maximum mass of a neutron star, which is how massive based on your TOV solvers, give or take? 2 something, right? Gravitational, right about 2-ish, a little higher. So let's say that we merge, the product of that is less than the maximum mass. But it's going to be rapidly rotating, right? Because you took these 2 neutron stars, spun them down. So that angular momentum's got to go somewhere. It gets radiated in gravitational radiation. It gets carried off by some of the ejecta, because there is tidal ejecta as well as shocked ejecta from the neutron star merger. But the bulk of it's going to go into the merger product. And so that thing is spinning, right? And it's differentially rotating. And in that case, you can get shear from the differential rotation that generates viscosity. And so you can model the transport of the angular momentum out from the neutron star using viscous Navier-Stokes equations like this. Right? And you can even parameterize your ignorance about what is leading to the physical viscosity, right? This depends on your physics right here, right? So you can parameterize this and parameterize your ignorance of this, and then solve those equations. There are those equations. So he did this and mapped out how quickly you can shed angular momentum from a hypermassive neutron star. Suffice to say, these get used. It's useful. It's not easy. And David is really, really, really good.
So In the top one, we used the polytropic equation.
Yes, that's correct.
So what's the generalization to general?
So we would have to use the other form of the energy equation where we didn't make this already the assumption of a gamma law. These terms are not different. This term is different. And I don't know off the top of my head. So I think what this would turn into is a thermodynamic derivative based on your general equation of state. So I'm not going to derive this correctly on the fly. But gamma for a general equation of state would be partial P partial rho at constant entropy. Yeah. And so if you had a general equation of state that was not gamma law, you'd get that, you substitute in this. This is related to the sound speed, right? In fact, this is almost the sound speed squared. It's the logarithmic derivative that's the sound speed squared, right? So what am I saying? So this is P over rho sound speed squared, right? And so I think you could substitute that in right there. And then once you relax this E star definition and substitute it back in the general expression for energy, not this reduced energy that comes from a gamma law. Yeah, this term would be different, but this would be what you could use for gamma in a general equation state. I think it would then end up being the same. This term is going to be the same.
Probably harder to solve.
Oh yeah. Yeah. Yep. But probably look at Dobbin's paper for this actually, because he did a general equation of state for a neutron star, not a polytrope. Yep. Erase that because it's probably wrong. Okay, cool. Good question. All right. Next thing. Heat or radiation diffusion. All right. So the stress energy tensor, then in this case, if I've got a scenario where heat is being transported by some conductive physics, I can write down the stress energy tensor for that heat as UA QB plus UB QA, where Q is equal to lambda TH minus sign PAB, my expansion tensor, gradient BT plus TA sub B. This is the heat flux. Q is the heat flux. So that's a flux of heat where now T without any indices at all. This is not the contraction of the stress energy tensor. This is the temperature, the thermal temperature. And A is the UB grad B UA is the fluid acceleration or acceleration. Okay. And then finally, lambda thermal is equal to the coefficient of thermal conduction. Like that. Okay, so that's pretty simple. This is parabolic. Solve it that way. I actually haven't written down the evolution equation. I'm getting there. But that's the stress energy tensor that arises from some heat in the system. And obviously, in the limit where the coefficient of thermal conduction is 0, no conduction, this is 0. You get no addition to the stress energy tensor then. So it's only the case where there's some physics that is conducting heat that you worry about this. Okay, so in the diffusion approximation, right, where we assume that the heat is transported by particles that are moving on random walks, characterized by some length scale. This thermal conductivity coefficient is equal to 4/3 B sub r T to the 3 all over chi bar, where B sub r is a radiation constant. Radiation constant. Here I'm assuming that the heat is being transported by particles that behave like radiation. So I should say that, right? Let me put that up here. For radiation. Okay. Specifically, you could have electrons conduct heat, other particles can conduct heat. Here we're talking about thermal radiation. So B sub r is a radiation constant, and it is equal to what I'll call little b, which is 8 pi to the 5th Boltzmann constant to the 4th, all divided by 15, I'll put this in parentheses, times speed of light cubed h Planck's constant cubed for photons. Cool. If you don't care about the numerical value, who cares about the numerical value? 7.56 times 10 to the minus 15 from memory. Okay, so now you're going radiation. Why did he specify photons? What else can act like radiation and conduct heat? Neutrinos. Photon is light.
Or light bosons.
Light bosons. Sure, totally. That could work. I was getting the neutrinos. So the other thing that can behave in relativistic media that we all care about, like photons and conduct heat in a diffusive way, is also neutrinos. And the constant here, the radiation constant, is slightly different. Br is equal to 7/16 B for, ready for this, non-degenerate neutrinos. Neutrinos. I can spell that. I only do it a billion times a day. Which are in equilibrium with the matter, meaning their chemical potential is 0. Now, why did I have to specify non-degenerate neutrinos? What the heck do I mean by that? Why does that matter?
Because they have to have different masses, or they can't be occupied in the same state.
There you go. What's that called?
Degeneracy.
Sure. Pauli exclusion, right? Because they're leptons. Photons are bosons, right? And so they can't block each other, right? They can be they can't be degenerate, right? But since neutrinos are leptons, they obey Pauli exclusion, and you can actually get conditions where the neutrinos become degenerate and they block each other from certain energy states, and that will change this value and lots of other things about the problem.
Do different flavors obey the exclusion principle, or do they have to be the same flavor too?
They can only block each other. If they're in a different flavor state, then they have different blocking properties. They all have a different chemical potential.
But then they can change between flavors too.
Shh, quiet you. We don't talk about that. Yes, they can. One of my postdocs is working on that in problems that we care about. That's a really hard problem. Okay. Oh, I didn't define chi. Chi bar is the Roslin mean opacity. Opacity. I'll just abbreviate that. That's what chi bar is in this equation. And that depends on microscopic properties of the medium. You usually have to look that up. You know, for certain cases, it's easy. If you're dealing with just, hey, it's just electron scattering. Okay, Thomson opacity, I can put that in. I know exactly what the Rosalind mean opacity is. In that case, I can express it analytically. I'm done. But in most interesting cases, this Rosalind mean opacity is more complicated and depends on microphysical parameters of the system you care about. Okay, last thing. We'll get through this and then we'll talk about pyro. These equations, what we just derived, are in the diffusion approximation. When is the diffusion approximation valid? When there's not much what?
Convection.
Convection. Sure. That another means of transporting the energy, right? Of moving the particles. So they could move convectively and move heat, but also if the medium is not optically thick, right? So if that Rosalind mean opacity is very small, such that the particles that are moving the energy are not so much impeded by the matter, they will just free stream away. And that's not diffusion, right? Diffusion requires that they obey a sort of random walk through the medium. But as you get closer and closer to not being optically thick, no longer is a random walk where the particle could be scattered in any direction with equal probability. No longer is that true, right? They'll start to prefer to be scattered in one direction until they don't scatter anymore and they just go off in a straight line. We call that the business being a highly forward peaked radiation field. In those cases where you can't just assume either of the limits, right? Where you can't assume it's completely free streaming, where I know that the photons or the radiation or the neutrinos are just going to travel on a straight line, or a geodesic in a curved space-time, which matters. And I can't assume that they're diffusive completely. I have to do what we call radiation hydrodynamics, where I've got to solve the full set of equations in a more general form, coupled together. In this case, the radiation stress energy tensor, TAB rad, looks like this. Double integral of d nu d omega I sub nu big NA big NB, where I nu is equal to the intensity as a function of space and direction, which I'll define in a second, and frequency. This is the specific intensity of the radiation. By definition. Okay. Now that's the specific intensity of radiation at some point x with some frequency nu moving in some direction in I. Okay. The units are crazy, and I didn't write them down. I should have done that. It's like ergs per second per steradian per centimeter for the frequency, or seconds. I should have wrote them down. Doesn't matter. Relativistically, the units are 1. Okay. And this unit vector is the direction vector is the momentum divided by h nu, where the PA is the momentum 4 vector. 4 momentum, okay? So dividing by the energy of the photon or the neutrino, right? So I'm just getting direction, right? Momentum divided by energy. It's just the direction they're moving in, essentially. And d omega is the solid angle. And so this integral to get the stress energy tensor is over all frequency, all solid angle. So if I go to some point in space and I want to know what is the stress energy tensor due to radiation at that point, well, I need to integrate all the little radiation packets that I find at that point over frequency, and then also integrate all over solid angle so that I account for all energy moving through that little parcel of space, right? As I integrate over solid angle. Okay. And the frame here matters, meaning who measures this matters. So in this case, my definitions here for I nu, for the frequency, and even for the solid angle are in frame of an observer with 4 velocity u a. All right. So some observer moving with some 4 velocity for ua. And I can pick frames, and the frames that I solve certain parts of the equations in could be different even. Certain things are easier to solve either in the fluid rest frame or in the laboratory frame, where I let the fluid move through the frame, right? That matters. Okay. All right. Start to build up towards solving the transport equation, but first we'll start with some easier stuff. Radiation, phase, space, distribution function. And this is F. You might have seen this before. Anytime something's a distribution function, we just use little f, right? That's speed of light squared over Planck's constant to the 4th, all times the specific intensity I nu over nu cubed. And this is Lorentz invariant. Handy feature. Why is that handy? See reference about frame matters. So if I'm transforming between different frames to do different parts of the calculations, I can use the fact that the distribution function is Lorentz invariant to help me do that. Okay, straw picture. Give my blue marker a rest. All right, so just to get a wee sense of this, let's pick some point in free space. Now, I'm going to assume that the radiation field, the distribution function, the specific intensity, let's assume that it's spherically symmetric, meaning that in a spherical coordinate system, it depends only on the radial coordinate. It doesn't depend on theta and phi. That's what I mean by spherically symmetric. So in this case, let's draw from my little point here. We're going to have out from here the radial vector, the radial unit vector. I'm just going to call it r hat for convenience. And now in this coordinate space, I can draw, we'll find out, some other direction, okay, with unit distance, let's say. And the angle between this unit vector and the radial direction, I'm going to call capital theta. I'm going to call that capital theta. And now that can have some angle relative to the radial direction. Normal to the radial direction, I'm going to call that, there's going to be some angle there. So I'm going to take a normal to the radial direction, right? So if my index finger is radial, this normal is my thumb, right? It goes around like this, okay? There's going to be some angle between that vector and, and this direction that I picked here, right? It doesn't matter, whatever that is. And I might call that capital phi. So in spherical symmetry, in this case, right? You guys get the sense of that geometry there? And then I can have some other, my middle finger can go any way it wants relative to the radial direction, like that. So in this, in spherical symmetry, like this, The radiation field depends only on this capital theta direction. Depends only on the angle away from the radial direction. Right? Because that's the way, you know, like, imagine yourself suspended in the atmosphere of a star, right? My head's pointing up towards the surface of the star. My feet are pointing down towards the center of the star, right? As I look up and then I look down, what do you think happens to the intensity of the radiation field? I start looking up, look down. What happens to the intensity?
You feel more intense.
Sure, changes. Now what happens if I look like this? Imagine that the star is much, much bigger than I am. Nothing, right? Like in this direction, that's the normal to the radial direction. The intensity is the same. This way, it changes quite a bit. Don't look down, look up.
So large phi is in the normal plane.
That's right. That's what I meant. I don't know that my drawing quite captures that, but that's what I meant. It's always normal to the radial direction. The 0 point of that, it's just the azimuthal direction. You can pick any direction along this azimuth to be 0. Doesn't matter. But I meant that to be azimuthal. Okay, so there's no dependence on the azimuthal direction. So in this case, let's define mu to be the cosine of big theta, often called the direction cosine, right? Which means that my specific intensity, I nu, will be equal to a function I nu of time, radius, and mu in spherical symmetry, right? Where obviously there's a time component. The radial coordinate tells me where I am in the space because it's symmetric in theta and phi. And then this tells me everything I need to know about the direction from which the radiation is coming and going. Okay. So now we can define, this is actually going to be somewhat general, just in spherical coordinates. Now, this doesn't actually require that it be spherically symmetric, but in the coordinates of t, r, theta, and phi, I can define moments of I nu as follows. I, which is just going to be equal to the frequency space integral of I nu, call that the mean intensity. Next one, E, which is a function of t and r in spherical symmetry, let's say. Here I am dropping the dependence on theta and phi in this expression. But you can write this down without spherical symmetry, actually. But I'll just do it with spherical symmetry for the moment. Double integral, 2 pi times the double integral of d nu, d mu of the intensity. You do that, we're going to define the radiation energy density. This is the energy density. Do it again. F of t and r. 2 pi double integral d nu, d mu, I nu. Where did I put this? Doesn't matter. But after the d mu, put a mu. Okay. No mu's, 1 mu. This is the radiation flux. The energy flux, radiation energy. One more. P of T and R is equal to 2 pi double integral d nu d mu a couple of mu's, mu squared, I nu. This is the radiation pressure. Like that. This is a moment expansion, a moment hierarchies, right? I'm going to higher orders in mu. That's all it is. Okay. I guess I did have plenty of stuff to get through today. Stuff's hard. Okay. A few other things then. Let's do the evolution equations. All right. So in our, if we define basis vectors, let's take some basis vectors in spherical, kind of general, write them generally as a set of basis vectors, EA, T hat, EA, R hat, EA, theta hat, using the notation that the book uses for basis vectors, phi hat, close bracket. So with this set of basis vectors then, I can plug this in to my radiation stress energy tensor and solve for the components of the stress energy tensor in terms of these moments of the specific intensity. When you do that, you get the following: TA hat, B hat, right. Now, recall that when I put hats on things, that means that I picked a basis. We're no longer in abstract index notation. The hats mean I have chosen a basis. It's like, you know, the form of the traveler has been chosen. Ah, someone got it. All right. E, F, 0, 0. F, P, 0, 0. 0, 0. 1/2 E minus P, 0. 0, 0, 0. 1/2 E minus P. So in this basis in spherical coordinates, I can actually write down my stress energy tensor for the radiation in terms of the moments, which means I need to solve for the moments. If I then want to incorporate this into an evolution for the radiation hydrodynamics, well, okay, cool. I've got this, but now I need to solve for the moments. The moments obey an evolution equation, which is going to look pretty familiar, sort of. Divergence of the stress energy tensor of radiation, but now I've got a source term, minus GA. And this GA encapsulates the interactions with matter. And so that looks like GA is equal to integral d nu d omega over solid angle of chi nu I nu minus eta nu close direction vector in A. And this is the radiation force. This is the force acting on the radiation field. And these are matter terms, right? This is the total opacity at frequency nu, right? As opposed to the Rosalind mean opacity, which had the bar on it. So this is the specific, the intensity, or I'm sorry, the frequency dependent opacity. And then this is the emissivity, all right? So destruction, creation. Destruction, creation, right? So how much radiation energy is the material emitting is encapsulated by the emissivity. If you were then to incorporate this into, I can remember these, the hydrodynamics, and ask what's the impact then on my matter stress energy tensor due to the radiation field, that looks like this. So then for the fluid, what happens is my divergence of my fluid stress energy tensor has got to be equal to minus the divergence of the radiation stress energy tensor, which is equal to GA. In other words, what comes out of the matter must go into the radiation. What comes out of the radiation must go into the matter. The stress energy must be conserved, right? That's all this is saying. That's it. Okay. And in general, then when you plug this in, you must solve for both parts of these simultaneously. Right? You must evolve them together. And the radiation stress energy tensor depends on the specific intensity through these moments, if you were to write it down in this moment formalism. And what we haven't written down is how do I solve then for the specific intensity at some point, right? These were not solutions to the specific intensity. They're re-expressions of the specific intensity in convenient forms. But I still need to solve for this specific intensity or come up with a way for doing that. I guess we will talk about that next time. And you also have to solve that then together. And that involves solving a transport equation or a Boltzmann equation or something like that. Same thing, to get the specific intensity and then solve for the moments. And on top of all of that, so I've got to solve for the fluid simultaneously with the radiation. I've got to come up with some transport solution to get me I nu. I also have to solve for the space-time, because the radiation contributes to the space-time. Anything that has stress energy contributes to the curvature of space-time, right? So radiation can curve space, right? Even though photons are massless, they're not energy-less, so they can curve space. Yeah, and this is starting to get at a lot of the pieces of the problems that we work on. Okay. I guess that's all I had in terms of notes. It took me a while to go through just a few pages of notes today. We can talk. I don't think I have time to plug my laptop in, but what I will do is I'll put together a little info sheet on what I'm thinking on Pyro, and I will send you links to Pyro stuff, and maybe we'll just have a quick little assignment. We might even talk about it then on Thursday of just playing with Pyro. It's really fun. Right? You can just pull it up in Python, run from a Jupyter notebook if you wanted to. But it's really easy to use and pretty slick little neat code. And we'll talk about that next time. I'll actually, I thought I would end like half an hour ago today. Am I moving slower? Was I talking slower today? I feel like I'm moving through a fog. I'm a little under the weather. This stuff just takes a while, I guess. What could be easier though? Yeah, I think next time then we'll talk about Pyro and we'll plot a course. And I'll plan on talking about the details of radiation hydrodynamics and also magnetohydrodynamics then. If it takes us 4 lectures to get through this chapter, it takes us 4 lectures. That's fine. I like stuff with matter. Who cares about black holes? Boring. Any questions? Okay, cool. I'll send you some info about Pyro that I hope that you touch on next time. Okay, thanks.